Alright, good evening. This lesson is over system and slopes, which is falling under the module application of Newton's laws. So we're going to go ahead and jump right into it, and I'm going to go through some example problems as well. The first thing is I kind of created a step for you on how to create these and solve these problems. So when we deal with two or more objects that are connected, you're first going to have to draw that free body diagram for each object. Make sure you write the equations for each object, and then you're going to combine equations for each object. And then finally, you're going to make sure that the internal forces should disappear when the equations are combined if you're doing it correctly. Oh gosh. Alright, let me make sure, yeah. Okay, so we're going to jump right into an example problem. It says the two boxes are arranged so one is on a table and it is connected to a second by a rope that passes over a pulley and it's attached to a second box. The second box is not in contact with any surface. Box A has a mass of 75 kilograms. And box B has a mass of 40 kilograms. There is a coefficient of friction between box A and the table. So remember, this is a table right here, but there's nothing under this box. And that coefficient of friction is 0.250. So the first thing that we're going to have to do is draw the free body diagrams for each box. So for box A, again, let me change my color. I meant to do this every time and always forget. We have that weight that's pulling down, and again the normal force pulling up. We have the tension pulling the box to the right, and then the friction going in the opposite direction. The free body diagram box for B would just be the box, the weight pulling down, and the tension pulling up. So that box is not moving horizontally. Next, we need to write the equations for box A and box B. So in the x-axis for box A, we're going to have that tension minus the friction, and you're going to that's going to equal to that mass times acceleration. For the y-axis, you're going to take that normal force minus the weight, and that's going to equal to 0. For box B, again, box B is the one that is dangling, and again, box A is the one that is being pulled. Write the equations for box B. So the y-axis, because it's not moving horizontally, we don't have to do the x-axis. We have that weight minus the tension equals mass times acceleration. And again, the B is just for box B, and the A's down here are just for representing box A. So now it wants us to calculate the normal force on box A. So we plug in our equation, we plug in what we know, and this is what we're going to find out. We have 75, which is given to us in the problem. Multiply that by gravity, and so we're going to have a normal force of 735 newtons. For box B, it's asking us to calculate the force of friction, for letter B. Second part of this, calculate the force of friction on box A. So again, remember box A had a tension pulling this way, which means that there is a friction in the opposite direction. It's given us the coefficient in the problem. So we're going to add those numbers together. The normal force, which is what we just calculated, we plug it in, and we're going to get 184 newtons. So now it's saying, what is the acceleration of the systems using clockwise around the pulley as your positive direction? So now we're going to have to add the equations for the axis of motion. So x for both box A and y for box B. So how we do that is by adding that tension minus friction equals mass times acceleration, and then we have the weight of box B minus the tension equals mass times acceleration. So if we add those formulas together, we're going to get the tension minus friction plus the weight of box B minus the tension equals the mass of box B times acceleration plus the mass of box B times acceleration, because we're adding this side of the equations and then adding this side of the equation. That's how we got that one. So we'll simplify it here by just rearranging some of the formulas, and now we're going to solve for the acceleration. We plug in what we know, so we have 40 kilograms times gravity minus 184, that's what we just calculated, the friction, divided by 75 plus 40, and that's all given us in the problem. And we're going to get an acceleration of 1.81 meters per second squared. Now it's going to ask us to solve for the tension of the rope. So we're going to solve using either equation in the axis of motion. So again, we know these formulas from the previous, and we're just going to plug in what we know. 75 times 1.81 plus 184. So these are all coming from the previous problems that we solved. And we're going to get 320 newtons. Or, for box B, we're going to plug in what we know. 40 times 9.8 minus 40 times 1.81. And we're going to get the same thing. So either way you could solve for the tension of the rope. And we know that these two tensions are going to equal each other because those boxes are not moving. They were stationary. Alright, so now we're going to move to slopes. So an object is moving down an incline. It is easy to rotate the axis so that one axis is parallel to the slope, and then we can solve the problems. The angle is always the slope given, and the weight must be broken down into the horizontal and vertical components. Again, if you don't see the triangle here, the weight is going to be pulling down the gravity, but we can break it into vertical and horizontal components compared to the surface. And there's your triangle that you can solve for your vectors down here. So here is a slope example. We have a 40.0 kilogram mass is placed on an inclined plane that makes an angle of 30 degrees to the horizontal. The coefficient of friction between the surface and the box is 0.15. Draw the FBD. So here is the box on an angle. We have the weight pulling it straight down. The normal, again, is always perpendicular to the surface, and then the friction is going to be in the opposite direction of the movement. So now we're going to draw the free body diagram with the components of the weight. So after we break it down, we have the weight, which is going to be perpendicular, and then the weight, which is going to be parallel. So that's what those little signs are. I'll try to draw them better for you up here. That's perpendicular, and then the weight that is parallel. So now we need to write the equation for parallel axis. So we have that weight for parallel minus the friction equals mass times acceleration, and we can expand it now or later by using mass times gravity, because again that's the weight, sine theta, because we have to find the components there, minus the friction equals mass times acceleration. Next we need to write the equation for the perpendicular axis. So that's going to be the normal minus the weight equals 0. We can expand it because we're going to have to find that vector component. So we have the normal minus the mass times the gravity cosine theta. So now we can calculate by adding in what we know. The mass times the gravity, 40 times 9.8, cosine 30, which is all given us in the problem. So we're going to get 339 newtons. And then we can calculate the force of the friction on the box. The coefficient of friction is given to us in the problem, which is 0.150 newtons times 339, which is what we just calculated over here, and we're going to get the force of the friction of 50.8 newtons. Last, it wants to calculate the acceleration of the box. So we have mass times gravity, the sine theta minus F equals mass times acceleration. If we plug in what we know, we have 40 times 9.8 sine the angle, again the angle is always the slope, minus 50.8, and we're all going to divide that by 40, and if you plug that into your calculator, we should get 3.63 meters per second squared. That is it for the review on slopes. Please let me know if you have any questions.